Probability addition rules. Mutually exclusive events. E and F are mutually exclusive or disjoint events if E and F have no outcomes in common. So if E and F are disjoint, this means that E and F is the empty set. That is, it has no outcomes. So the probability of E and F is 0. It is an impossible event. The sample space, suppose, is the numbers 1 through 10, and assume that each number is equally likely. Let's define A to be the set of even numbers in that sample space 2, 4, 6, 8, and 10. Then the probability of A, since all outcomes are equally likely and there are 5 outcomes in A, is 5 over 10, or 0.5. Suppose that B is the set of prime numbers in that set, 2, 3, 5, and 7. Then the probability of B is 4 out of 10, or 0.4. Then A and B is the set of all elements in A as well as in B. And we could see that the only number that's in both A and B is 2. So we say A and B equals 2. And the probability of A and B is just 1 out of 10 because it just has one element. So the probability of A and B is 0.1. Now A or B is the set that consists of numbers that are in either A or B, or both. So A or B will have 2, 3, 5, and 7 from B, and 2, 4, 6, 8, and 10 from A, but 2 is not listed twice. Each element should only be listed once. A or B has 8 elements, so the probability of A or B is 8 out of 10, or 0.8. Now notice how the probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. We could see that because 0.8 is the probability of A or B, 0.5 is the probability of A, 0.4 is the probability of B, and 0.1 is the probability of A and B. I needed to subtract the probability of A and B in order to avoid double counting the 2, which happen to appear in both A and B. The addition rules are the following. First of all, if E and F are any events, then the probability of E or F equals the probability of E plus the probability of F minus the probability of E and F. That was just the equation we had in the last slide. However, if E and F are mutually exclusive events, then the equation simplifies to the probability of E or F equals the probability of E plus the probability of F. You don't need to subtract the probability of E and F because that probability is 0 when you have mutually exclusive events. Suppose that I want to find the probability of W and V, and I'm given that the probability of W or V is 0.85. The probability of V is 0.7, and the probability of W is 0.3. Well, I go through my general addition rule because I'm not told that W and V are mutually exclusive. Therefore, I need to use my general addition rule. Probability of V or W is the probability of W plus the probability of V minus the probability of W and V. Now I know 3 out of those 4 quantities, so let me substitute the known values in. 0.85, 0.3, 0.7, and I'm just going to rewrite the probability of W and V, the only unknown. 0.3 plus 0.7 is 1, and then if I subtract 1 from both sides, I get negative 0.15 equals negative probability of V and W. I multiply both sides by -1 and I get 0.15 equals the probability of W and V. Sometimes I say the probability of W and V, sometimes I say the probability of V and W. They mean the same thing, the order does not matter. So I say the probability of V and W is 0.15, and that will be my answer. Suppose that the sample space again is the numbers 1 through 10, and again each outcome is equally likely, and again B is just the set of prime numbers in that set, 2, 4, 5, and 7, then the probability of B is 4 out of 10, or 0.4. Now we have B with a C, as it looks somewhat like an exponent. This is pronounced B complement. B complement. B complement is the set of all elements that are in the sample space but are not in B. The set of all elements that are in the sample space but are not in B are in B complement. Now, you could see that B complement has 6 elements, so the probability of B complement is 6 over 10, or 0.6. And we could also see the complement rule. The probability of B complement is 1 minus the probability of B. This holds in general. This holds for any event B.